It happened on August 24th, 2006. A group of astronomers gathered in Prague for a meeting of the International Astronomical Union, or IAU. This is the group that gets to name things in space. On that day, they took a vote. The vote was about what it means to be a planet. For decades, every school kid learned there were 9 planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But astronomy had moved on. They had found other objects out past Neptune. Some were even bigger than Pluto. One called Eris, discovered in 2005, was more massive, so the IAU had a choice. Either they had to add dozens of new planets to the list, or they had to define the word planet more clearly. They chose to define it. The new definition had 3 rules. A planet must orbit the sun. It must be big enough for gravity to make it round, and it must have cleared its neighborhood of other objects. Pluto failed on that last rule. It lives in a crowded area called the Kuiper Belt. So with a vote, Pluto was demoted. It was now a dwarf planet. The news was a shock to many people. It felt like a piece of childhood was suddenly wrong, but it wasn't really. It was just science correcting itself. It was an admission that what we thought we knew was incomplete, and that's what science does. It learns more, and sometimes that means changing the old facts. That Pluto moment in 2006 was a very public example of something that happens all the time. The facts we learn in school are often simplified. Sometimes they're just plain wrong. They are snapshots of what we knew at the time, but the picture keeps getting clearer. And when it comes to space, a lot of what we think we know is due for an update. For number 20, the sun is not yellow. The sun is actually white. Astronauts in space see it as a brilliant, pure white star. The only reason it looks yellow, orange, or red to us is because of Earth's atmosphere. Our atmosphere acts like a filter. It scatters light. This effect is called Rayleigh scattering. It's the same reason the sky is blue. Light from the sun is made of a spectrum of colors, just like a rainbow. Blue and violet light have shorter, smaller waves. Red and orange light have longer, wider waves. The tiny molecules of gas in our atmosphere, mostly nitrogen and oxygen, are the perfect size to scatter the shorter wavelength blue light. As sunlight streams through the air, the blue light gets bounced around in all directions. This scattered blue light fills the sky, making it appear blue to our eyes. But what about the sun itself? With a lot of the blue light scattered away, the remaining light that comes directly to our eyes is a bit weaker on the blue end of the spectrum. This leaves a yellowish tint. The effect is even stronger at sunrise and sunset. When the sun is on the horizon, its light has to travel through much more of the Earth's atmosphere to reach you. This means even more blue light gets scattered away. It also starts scattering green and yellow light. All that's left to reach your eyes are the longest wavelengths, the oranges and reds. This is why sunsets and sunrises are so colorful. If you were on the International Space Station, high above the atmosphere, there would be no scattering. You would see the sun for what it is. A blindingly white ball of plasma. Astronomers classify stars by their color, which tells them its temperature. Our sun is a G-type main sequence star, often called a yellow dwarf. Its official spectral type is G2V. The G2 part tells you its surface temperature is about 5,778 Kelvin, or 9,940 degrees Fahrenheit. Stars in this temperature range do emit most strongly in the green-yellow part of the spectrum, but they also emit huge amounts of light in all the other colors too. When our eyes see all these colors mixed together at full intensity, it registers as white. Our brains are wired to see the sun as the baseline for white light. It's just that we almost never get to see it unfiltered. Even the photos you see of the sun are often colored yellow for cultural reasons. We are just so used to drawing it with a yellow crayon that we make our pictures match our experience on the ground, not the reality in space. The sun is also not a peaceful, steady ball of fire. It's a churning, violent place. It's made of plasma, a superheated gas of charged particles. This plasma is constantly in motion, creating powerful magnetic fields. These magnetic fields get twisted and tangled. When they snap, they can release enormous amounts of energy in the form of solar flares and coronal mass ejections. These events send streams of charged particles flying out into space. If they hit Earth, they can cause the beautiful northern and southern lights, but they can also disrupt satellites and power grids. The surface we see, the photosphere, is covered in granules, which are the tops of convection cells. Each one is about the size of Texas and lasts for only about 15 minutes before being replaced by a new one. It's like a pot of boiling water, but on a star-sized scale, so not only is the sun not yellow, it's far more complex and dynamic than the simple circle we drew in school. Number 19, Mercury is not the hottest planet. Venus is the hottest planet in our solar system. Its average surface temperature is a staggering 864 degrees Fahrenheit, or 462 degrees Celsius. That's hot enough to melt lead. Mercury, on the other hand, is the closest planet to the sun. It makes sense to think it would be the hottest, and it does get very hot. Daytime temperatures on the side facing the sun can soar to 800 degrees Fahrenheit or 430 degrees Celsius. But Mercury has a secret. It has almost no atmosphere. An atmosphere acts like a blanket. It traps heat and distributes it around the planet. Without one, Mercury can't hold on to the heat it gets from the sun. So when night comes to Mercury, the temperature plummets. It can drop as low as minus 290 degrees Fahrenheit or minus 180 degrees Celsius. That is an incredible temperature swing of over 1,000 degrees Fahrenheit from day to night. This is one of the most extreme temperature differences in the whole solar system. Venus is different. It is the second planet from the sun, about 30% farther away than Mercury, so it receives less direct sunlight, but it has an incredibly thick, toxic atmosphere. Its atmosphere is about 90 times denser than Earth's. It's mostly carbon dioxide with clouds of sulfuric acid. Carbon dioxide is a greenhouse gas. It lets sunlight in, but it doesn't let heat out. This has led to a runaway greenhouse effect on Venus. Over billions of years, the heat has built up with no way to escape. The thick atmosphere is so efficient at trapping heat that the temperature is nearly uniform across the entire planet. There is almost no difference between day and night, or between the equator and the poles. It's just always 864 degrees. The pressure on the surface of Venus is also immense. It's over 92 times the pressure of Earth's atmosphere at sea level. It's the equivalent of being about 3,000 feet deep in the ocean. Any spacecraft that has landed there has been crushed and cooked within a couple of hours. The Soviet Union's Venera 13 lander survived the longest for 127 minutes in 1982. It sent back the first color photos from the surface of Venus, showing a bleak orange, rocky landscape under a thick yellow sky. So while Mercury is the closest to the sun, it's Venus's killer atmosphere that makes it the hottest place in the solar system, aside from the sun itself. It's a powerful lesson in how a planet's atmosphere, not just its distance from its star, determines its climate. It's a stark example of what can happen when the greenhouse effect goes completely out of control. It's a reminder that the story of a planet's temperature is more complicated than just its position in the lineup from the sun. Number 18, gravity is everywhere in space. There is no zero gravity in space. This is one of the biggest misconceptions. When we see astronauts floating on the International Space Station ISS, it looks like they are weightless because there is no gravity. But that's not true at all. The ISS orbits at an altitude of about 250 miles or 400 kilometers. At that height, the Earth's gravity is still incredibly strong. It's about 90% as strong as it is on the surface. If you could somehow build a tower 250 miles high and stand on top of it, you would feel only slightly lighter than you do on the ground. You certainly wouldn't float away. So why are the astronauts floating? They are in a constant state of freefall. The ISS and everything inside it is falling towards the Earth, but it's also moving sideways very, very fast. It travels at about 17,500 miles per hour or 7.8 kilometers per second. That sideways motion is so fast that as it falls, the Earth curves away beneath it. It is constantly falling, but it never hits the ground. This is what an orbit is. It's a continuous fall around a planet. Think of it like being in an elevator when the cable snaps. For the few seconds you are falling, you and everything else in the elevator would be weightless relative to the elevator car. You could float in midair inside the car. Of course, the end of the ride would be a problem. For astronauts on the ISS, their fall just never ends. They are always falling and the station is falling with them, and so they feel weightless. This state is more accurately called microgravity, not zero gravity. True zero gravity would only be found in the vast emptiness of intergalactic space, infinitely far from any star or planet. And even there, the tiny gravitational pull from distant galaxies would still exist. Gravity has an infinite range. It gets weaker with distance, but it never truly disappears. The moon's gravity pulls on Earth's oceans, causing tides. Earth's gravity keeps the moon in orbit. The sun's gravity keeps all the planets in orbit. The galaxy's gravity keeps the sun in orbit. It is the fundamental force that organizes the universe on a large scale. The experience of microgravity has profound effects on the human body. Without the constant pull of gravity, bones start to lose density. Muscles begin to atrophy. The cardiovascular system gets lazy because it doesn't have to work as hard to pump blood uphill to the head. Astronauts have to exercise for about 2 hours every day just to combat these effects. So the next time you see astronauts floating, remember they are not in a place without gravity. They are riding a 17,500 mile per hour fall around our planet, held in place by the very force it seems they have escaped. Number 17, the moon has a far side, not a dark side. The idea of a dark side of the moon is a persistent myth. The moon does have a side that we never see from Earth, but it is not permanently dark. It gets just as much sunlight as the side we see. A better name for it is the far side. The reason we only see one side of the moon is a phenomenon called tidal locking, or synchronous rotation. Early in its history, the moon rotated much faster than it does today, but the Earth's gravity exerted a pull on the moon. This gravitational pull created tidal bulges on the moon, similar to how the moon's gravity creates tides on Earth. The Earth's gravity tugged on these bulges, trying to slow the moon's rotation down. Over millions of years, this constant braking effect slowed the moon's spin until it reached a stable point. That point was when its rotation period matched its orbital period. The moon now takes about 27.3 days to rotate once on its axis. It also takes about 27.3 days to complete one orbit around the Earth. The result is that the same side is always facing us. Think of it like two dancers holding hands and spinning around. One dancer, the moon, spins exactly once for every one circle they make around the other dancer, the Earth. From the Earth's perspective, we only ever see the dancer's face. The back of their head remains hidden. But just like the dancer's back, the far side of the moon still gets illuminated by the sun. As the moon orbits the Earth, different parts of it are lit up by the sun. This is what creates the phases of the moon. When we see a new moon, the far side is fully illuminated. When we see a full moon, the far side is in complete darkness. The far side goes through the same cycle of day and night as the near side. A day on any part of the moon lasts for about 2 Earth weeks, followed by 2 Earth weeks of night. For all of human history, the far side was a complete mystery. No one had ever seen it. That changed on October 7th, 1959. The Soviet probe Luna 3 flew around the moon and took the first pictures of the hidden hemisphere. The images were grainy and indistinct, but they were revolutionary. They revealed a world that was surprisingly different from the near side. The near side is dominated by large, dark plains of volcanic rock called Maria, or seas. The far side has very few Maria. It is almost entirely covered in craters. It's more ancient and battered. The reason for this difference is thought to be the thickness of the moon's crust. The crust on the far side is significantly thicker than on the near side. This made it harder for magma from the moon's interior to break through to the surface and form the volcanic plains we see on the near side. In January 2019, China's Chang'e 4 mission became the first spacecraft to make a soft landing on the far side of the moon. It's exploring a massive crater called the South Pole Aitken Basin, one of the largest impact craters in the solar system. Because the far side is shielded from the radio noise of Earth, it's a prime location for radio astronomy. So there is no perpetually dark side, there is only a far side, which for millennia was hidden, but is now slowly giving up its secrets. Number 16, you would not explode in the vacuum of space. In Hollywood movies often get this wrong. A character's helmet gets cracked and they instantly swell up and explode in a gory mess. The reality of exposure to the vacuum of space is gruesome, but it's not that. You would not explode. Our skin is remarkably strong and elastic. It's more than tough enough to hold our bodies together against the lack of outside pressure. What would happen is something called ebullition. The pressure in a vacuum is so low that the boiling point of liquids drops dramatically. The liquids in your body, the saliva on your tongue, the moisture in your eyes, and the water in your blood and soft tissues would begin to boil. This doesn't mean they would get hot. It's a cold boiling caused by the low pressure. This would cause your body to swell up to perhaps twice its normal size, which would be very painful if you were conscious. But this is not an explosion. Your skin would stretch, but it would not rupture. The biggest and most immediate threat is the lack of oxygen. Space is a vacuum, meaning it contains virtually no air. You would have about 15 seconds of useful consciousness before you passed out from hypoxia. Before you lose consciousness, the air in your lungs would be a major problem. If you tried to hold your breath, the air trapped in your lungs would expand rapidly due to the pressure difference. This would rupture the delicate tissues of your lungs, forcing air bubbles into your bloodstream, which would be fatal. The first rule of surviving a sudden vacuum exposure is to exhale completely. After you passed out, you would die from asphyxiation within a minute or two. You would also be exposed to extreme temperatures. You might think you would freeze instantly. But that's also not true. While space is incredibly cold, a vacuum is a very poor conductor of heat. There's no air to carry heat away from your body. The main way you would lose heat is through thermal radiation, which is a relatively slow process. You would also be exposed to direct, unfiltered sunlight, which would cause a severe sunburn on any exposed skin. So you would be simultaneously getting sunburned and, slowly freezing. You would also be exposed to dangerous radiation like ultraviolet rays and cosmic rays, but these are longer-term dangers. The lack of oxygen would kill you long before cancer became a concern. We know some of this from real-world accidents. In 1966, a NASA technician was testing a spacesuit in a vacuum chamber when it suddenly depressurized. He remained conscious for about 14 seconds. The last thing he remembered was the feeling of the saliva on his tongue beginning to bubble. The chamber was repressurized quickly, and he survived with no lasting damage. There have also been accidents involving Soviet cosmonauts. The crew of Soyuz 11 in 1971 died when their capsule depressurized during re-entry. They were found in their seats having died from asphyxiation. Their bodies had not exploded. So while exposure to the vacuum of space is certainly deadly, the reality is a grim combination of suffocation and ebullition, not the dramatic explosion you see in the movies. Number 15. The asteroid belt is mostly empty space. Movies like The Empire Strikes Back have given us a dramatic image of the asteroid belt. We see spaceships dodging and weaving through a dense, chaotic field of tumbling rocks. It makes for an exciting scene, but it's completely inaccurate. The asteroid belt is, in reality, almost entirely empty space. The asteroid belt is a region between the orbits of Mars and Jupiter. It contains millions of asteroids ranging in size from tiny pebbles to the dwarf planet Ceres, which is about 590 miles, 950 kilometers in diameter. All of those asteroids sound like a lot, and it is, but the volume of space they occupy is immense. If you took all the material in the asteroid belt and squished it together, it would form an object with a total mass of only about 4% of our moon. The average distance between individual asteroids is huge. It's estimated to be over 600,000 miles, or about 1 million kilometers. That's more than 2.5 times the distance from the Earth to the moon. Flying a spaceship through the asteroid belt is not a dangerous maneuver. In fact, you would be extremely lucky to even see an asteroid up close. The chances of accidentally hitting one are astronomically small, far less than 1 in a billion. We know this for a fact because we have sent numerous spacecraft through the asteroid belt without any problems. The first was Pioneer 10 in 1972. Since then, probes like Pioneer 11, Voyagers 1 and 2, Galileo, Cassini, New Horizons, and others have all passed through the belt without incident. None of them had to perform any dodging maneuvers. The mission planners were not worried about collisions. In fact, when the Galileo mission wanted to study the asteroids Gaspra and Ida, it had to be carefully targeted to fly close to them. It would not have encountered them by chance, so why did the asteroid belt form in the first place? It's not the remains of a planet that exploded, which was a popular theory for a while. It's actually a planet that never got the chance to form. The gravitational influence of the massive planet Jupiter was just too strong. Jupiter's gravity constantly stirred up the material in that region. It either ejected the planetesimals from the solar system entirely, or caused them to collide with each other at such high speeds that they shattered instead of clumping together to form a planet. So the asteroid belt is not a crowded minefield. It's a vast, lonely expanse of space, sparsely populated by the rocky leftovers of a planet that never was. It's a testament to the powerful and sometimes disruptive role of gravity in the formation of our solar system. Number 14, space is completely silent. The famous tagline from the movie Alien was, "In space, no one can hear you scream." That line is scientifically accurate. Space is a near-perfect vacuum. For the most part, it is completely silent. Sound, as we experience it, is a mechanical wave. It needs a medium to travel through. On Earth, sound travels as vibrations through the air. The vibrations cause air molecules to bump into their neighbors, which bump into their neighbors, and so on, carrying the wave from its source to our ears. Our eardrums vibrate in response, and our brain interprets that as sound. In the vacuum of space, there are very few molecules. The space between stars is not perfectly empty. It contains a very thin plasma of gas and dust, called the interstellar medium. But the particles are so far apart that they can't effectively transmit vibrations. And an explosion might happen right next to your spaceship, and you would see a brilliant flash of light, but you would hear absolutely nothing. The light can travel through a vacuum, but the sound wave cannot. This is why science fiction movies that have loud, booming explosions and zapping laser sounds in space are taking artistic liberties. In reality, a space battle would be a silent, eerie light show. Astronauts in space can talk to each other, of course. They do this inside their spacecraft or station where there is a pressurized atmosphere of breathable air for sound to travel through. When they are on a spacewalk, they communicate using radios built into their helmets. The radio waves are a form of electromagnetic radiation like light, and they can travel through a vacuum just fine. Their voice is converted into a radio signal, transmitted to the other astronaut's helmet, and converted back into sound waves inside the helmet's atmosphere. So they hear each other, but not directly. While space is silent to our human ears, it is not without its own kind of sound. In 2022, NASA released a sonification of the pressure waves emanating from a supermassive black hole at the center of the Perseus galaxy cluster. The black hole creates ripples in the hot gas of the cluster. These are, in essence, sound waves. But They are at a frequency far too low for humans to hear. The pitch is about 57 octaves below middle C. NASA raised the pitch by quadrillions of times to make it audible. So there are pressure waves in space, but they are not sound in the way we think of it. For all practical purposes for a human being, the cosmos is a silent place. The roar of a rocket engine cuts off the moment it leaves the atmosphere. The universe unfolds in a magnificent, silent ballet of light and gravity. Number 13, black holes are not cosmic vacuums. Black holes have a fearsome reputation. They are often portrayed as cosmic vacuum cleaners, relentlessly sucking up everything in their path. This isn't quite right. A black hole is not a hole. It's an object. It's an enormous amount of mass packed into an incredibly small volume. The result is gravity so strong that nothing, not even light, can escape once it gets too close. The point of no return is called the event horizon. If you cross the event horizon, you are not coming back out. But outside of the event horizon, a black hole behaves just like any other object with the same mass. Its gravity is powerful, but it's not some kind of magical suction force. If we were to replace our sun with a black hole of the exact same mass, a strange thing would happen: almost nothing. Earth and the other planets would continue to orbit the black hole just as they orbit the sun now. The orbits would not change. We would, of course, freeze to death in the dark, but we would not be sucked in. The black hole's gravity at our distance would be exactly the same as the sun's is now. You have to get very close to a black hole for its extreme effects to become apparent. Things don't just fall straight into a black hole. More often, material goes into orbit around it, forming a swirling, superheated disk of gas and dust called an accretion disk. The friction and intense gravitational forces in this disk heat the material to millions of degrees, causing it to glow brightly in X-rays. This is how astronomers can see black holes. They don't see the black hole itself, but the effects it has on the material around it. If you did fall into a black hole, you wouldn't be sucked in like a piece of dust into a vacuum. You would experience something far stranger called spaghettification. As you got closer, the gravitational pull on the part of your body closest to the black hole would be much stronger than the pull on the part farthest away. This difference in gravitational force, called a tidal force, would stretch you out like a piece of spaghetti. For a smaller stellar mass black hole, this stretching would begin long before you even reach the event horizon. For a supermassive black hole like the one at the center of our galaxy, the tidal forces at the event horizon are much gentler. You could cross the event horizon without being torn apart. What happens after that is a complete mystery, as the laws of physics as we know them break down at the central point, or singularity. So black holes are not roaming the universe, hunting for planets to devour. They are simply the final collapsed remnants of massive stars or the ancient anchors at the centers of galaxies. Their gravity follows the same rules as everything else in the universe. They are extreme, but they are not magical. Number 12, the Earth is a lumpy, squashed ball. We learn in school that the Earth is a sphere. We see it in pictures from space, a perfect blue marble, but that's a simplification. The Earth is not a perfect sphere. It's not even a perfect spheroid. It's a lumpy, bumpy, and slightly squashed ball. The main reason it's not a perfect sphere is its rotation. The Earth spins on its axis once a day. This rotation creates a centrifugal force, which is strongest at the equator. This force causes the planet to bulge out around its middle. The result is that the Earth is an oblate spheroid. The diameter from the North Pole to the South Pole is about 12,714 kilometers, 7,900 miles, but the diameter at the equator is about 12,756 kilometers, 7,926 miles. That means the Earth is about 42 kilometers, or 26 miles, wider than it is tall. This isn't a huge difference on a planetary scale, but it's significant. It means that if you are standing at the equator, you are actually farther from the center of the Earth than if you are standing at one of the poles. And because gravity depends on distance, the pull of gravity is slightly weaker at the equator than it is at the poles. You would weigh about 0.5% less at the equator. Mount Everest is the highest point on Earth above sea level. But because of the equatorial bulge, the peak of Mount Chimborazo in Ecuador is actually the point on the Earth's surface that is farthest from the Earth's center. But the shape is even more complex than that. The Earth is also lumpy. The mass of the Earth is not distributed perfectly evenly. There are places with slightly more mass, like mountain ranges, and places with slightly less. These variations in mass create small variations in the gravitational field. Scientists use a model called the geoid to represent the true shape of the Earth. The geoid is a representation of the surface where the pull of gravity is the same everywhere. It's an idealized sea level that extends over the whole globe. A map of the geoid looks like a lumpy, misshapen potato. The bumps and dips are exaggerated for visibility, but they show the areas where gravity is slightly stronger, the bumps, or slightly weaker, the dips. These variations are measured by satellites that can detect tiny changes in the gravitational pull as they orbit the Earth. These measurements are incredibly important. They are used for everything from creating accurate GPS systems to understanding ocean currents and changes in ice sheets. So while blue marble is a beautiful and useful image, the reality is much more interesting. Our planet is a dynamic, rotating, and gravitationally uneven world. Its slightly squashed, lumpy shape is a record of its history and the physical forces that continue to shape it. Number 11, Earth's tilt causes the seasons, not its distance from the sun. It's a common and logical assumption. Summer is hot, so the Earth must be closer to the sun. Winter is cold, so it must be farther away. This makes intuitive sense, but it's completely wrong. The seasons are caused by the tilt of the Earth's axis, not its distance from the sun. The Earth's orbit around the sun is not a perfect circle, it's a slight ellipse. This means that our distance from the sun does change throughout the year. The point in our orbit where we are closest to the sun is called perihelion. It occurs in early January. The point where we are farthest from the sun is called aphelion. It occurs in early July. Notice the dates. The Earth is closest to the sun in January, which is winter in the northern hemisphere. It is farthest from the sun in July, which is summer in the northern hemisphere. This is the opposite of what you would expect if distance caused the seasons. This fact alone proves that the distance theory is incorrect. The real reason for the seasons is that the Earth is tilted. Its axis of rotation is not straight up and down relative to its orbit. It is tilted at an angle of about 23.5 degrees. This tilt means that for part of the year, the northern hemisphere is tilted towards the sun. And for the other part of the year, it's tilted away from the sun. When the northern hemisphere is tilted towards the sun's rays hit it more directly. This is like shining a flashlight straight down on a piece of paper. The light is concentrated in a small area, making it very intense and hot. The days are also longer. This combination of direct sunlight and longer days is what we call summer. At the same time, the southern hemisphere is tilted away from the sun. The sun's rays hit it at a more glancing angle. Or it's like shining the flashlight at an angle. The light is spread out over a larger area, making it weaker and cooler. The days are shorter. This is winter in the southern hemisphere. 6 months later, the situation is reversed. The Earth has moved to the other side of its orbit. Now, the southern hemisphere is tilted towards the sun, experiencing direct sunlight and summer. The northern hemisphere is tilted away, experiencing indirect sunlight and winter. The spring and autumn equinoxes are the points in between, when the tilt is neither towards nor away from the sun. On these days, the sun shines directly on the equator, and day and night are of roughly equal length all over the world. This axial tilt is why the poles experience such extreme seasons with 24-hour daylight in the summer and 24-hour darkness in the winter. And it's why the tropics near the equator have very little seasonal variation at all. The sun is always high in the sky there, so it is this simple, steady tilt of our planet that gives us the rhythm of the seasons, a cycle of change that has shaped life on Earth for billions of years. Number 10. A shooting star is a tiny rock burning up. When you see a bright streak of light flash across the night sky, it's easy to think it's a star falling from its place. The names we use, shooting star, falling star, reinforce this idea, but these beautiful events have nothing to do with stars. A shooting star is actually a tiny piece of space rock or dust, usually no bigger than a grain of sand, burning up as it enters the Earth's atmosphere. The correct scientific term for this streak of light is a meteor. The story starts with a meteoroid. A meteoroid is a small object traveling through space. It could be a fragment of an asteroid or a piece of dust left behind by a comet. There are millions of them in our solar system. When one of these meteoroids happens to cross Earth's path, it enters our atmosphere at an incredible speed. They can be traveling at speeds of 25,000 to 160,000 miles per hour, 40,000 to 257,000 km/h. At this speed, the friction with the air molecules is immense. This intense friction rapidly heats the meteoroid and the air around it. The meteoroid becomes incandescent, glowing brightly. It's this glowing trail of superheated air and vaporized rock that we see from the ground as a meteor. Most meteoroids are so small that they completely burn up and disintegrate high in the atmosphere, about 50 to 75 miles, 80 to 120 kilometry above the ground. On any clear night, you can expect to see a few sporadic meteors if you are patient and away from city lights. Sometimes we get a much better show. A meteor shower occurs when the Earth passes through the dusty trail of debris left behind by a comet. As the Earth plows through this stream of particles, we see dozens or even hundreds of meteors per hour. They all appear to radiate from a single point in the sky, called the radiant. Meteor showers are named after the constellation where their radiant appears to be. The Perseids in August radiate from Perseus. The Geminids in December radiate from Gemini. What if the object is bigger? If a meteoroid is large enough to survive its fiery passage through the atmosphere and actually hits the ground, it is then called a meteorite. Most meteorites are small, pebble-sized rocks, but occasionally a much larger object hits. These can create massive impact craters, like the famous Meteor Crater in Arizona, which was formed about 50,000 years ago by an iron meteorite about 150 feet across. So a shooting star is not a star at all. Stars are gigantic, distant suns, trillions of miles away. A meteor is a tiny, close visitor, a grain of cosmic dust, giving its life in a brief, brilliant flash just a few dozen miles above our heads. Number 9. You cannot see the Great Wall of China from the moon. This is a classic fact that has been repeated for generations. The Great Wall of China is so immense that it is the only man-made object visible from the moon. It's a romantic and impressive idea. It's also completely false. You cannot see the Great Wall of China from the moon. Not even close. Seeing the Great Wall from the moon would be the equivalent of trying to see a single human hair from 2 miles away. The moon is, on average, about 239,000 miles, 384,000 kilometers from Earth. From that distance, you can see continents, oceans, and major weather patterns. You cannot see any individual man-made structures. Even the Great Wall, which is very long, is also very narrow, only about 30 feet wide at its widest. From the moon, it is simply too thin to be resolved by the human eye. The myth probably started long before humans actually went to space. It was a way of expressing the sheer scale and permanence of the wall. But once we started sending people into orbit, we could check. Astronauts have confirmed it. You can't see the Great Wall from the moon, but what about from low Earth orbit where the space station flies? This is much closer, only about 250 miles up. Even from there, seeing the wall is incredibly difficult. Chinese-American astronaut Leroy Chiao looked for it many times from the ISS and never saw it. He took a photo of what he thought might be it, but it turned out to be something else. Other astronauts have reported that under perfect conditions, the right angle of the sun to create shadows, clear air, and maybe using binoculars or a zoom lens, it is possible to spot sections of it. But it does not stand out. It looks like a very fine, faint line. It's certainly not the prominent feature the myth suggests. Astronauts report that many other man-made things are far more visible from orbit. The pyramids of Giza can be seen, but mostly because of their distinct shape and the shadows they cast in the desert. Large cities are easily visible as grayish patches during the day and as brilliant webs of light at night. The most visible things are long, straight lines that contrast with their surroundings. Things like airport runways, highways cutting through deserts, and the long lines of irrigated fields like the grid patterns of green circles in the American Midwest. These are often more prominent than the Great Wall, which tends to blend in with the terrain around it. The myth is a powerful one because it speaks to a human desire to leave a mark on the world that is visible even from the heavens. But the reality is that our planet from a distance is a natural world. Our greatest engineering feat is, from a cosmic perspective, almost invisible. Number 8, astrology has nothing to do with astronomy. The words are similar, they both deal with stars and planets, but that's where the similarity ends. Astronomy is a science. Astrology is not. They are fundamentally different ways of looking at the cosmos. Astronomy is the scientific study of everything in the universe beyond Earth's atmosphere. That includes stars, planets, galaxies, black holes, and the origins of the universe itself. It is based on the scientific method. Astronomers make observations, use mathematics and physics to create theories, and then test those theories with more observations. It is a field of constant discovery where ideas are challenged and refined as new evidence comes to light. Our understanding of the universe, from the Big Bang to the existence of exoplanets, comes from astronomy. Astrology is an ancient belief system. It claims that the positions of the sun, moon, and planets at the time of a person's birth have a direct influence on their personality and destiny. It uses a set of rules and interpretations, many of which were established thousands of years ago, to create horoscopes and make predictions. Astrology originated at a time when humanity's understanding of the universe was very different. The Earth was thought to be the center of the universe, and the planets and stars were seen as divine or mystical. The constellations of the zodiac, which are just random patterns of stars as seen from Earth, were given special significance. From a scientific perspective, astrology has been thoroughly debunked. There is no known physical force or mechanism by which planets, which are millions of miles away, could influence a person's life in the way astrologers claim. The gravitational pull of the doctor delivering a baby is stronger than the gravitational pull of Mars. The constellations themselves are an illusion of perspective. The stars in a constellation are not actually close to each other. They are all at vastly different distances from Earth and just happen to line up in a particular pattern from our viewpoint. If you traveled to another star system, the constellations would look completely different. Another major problem for astrology is precession. The Earth wobbles on its axis like a spinning top. This wobble, called precession, causes the position of the constellations to shift in the sky over long periods. The astrological signs were defined over 2,000 years ago. Due to precession, the sun is no longer in the same constellation on a given date as it was back then. For about half the year, the Sun sign assigned by traditional astrology is off by one full constellation. For example, if your horoscope says you are a Scorpio, the sun was most likely in the constellation Libra or even Virgo when you were born. Numerous scientific studies have tested the claims of astrology. They have consistently found that there is no correlation between astrological predictions and actual life events or personality traits. Astrology's predictions are no better than random chance, so while astronomy is a science that expands our knowledge, astrology is a system of belief that has remained largely unchanged for centuries, despite all the evidence against it. One is a window to the real universe, the other is a mirror reflecting ancient human hopes and fears. Number 7, there is no ninth planet anymore. For over 70 years, we learned there were 9 planets. The list was a piece of basic knowledge. But in 2006, that changed. Pluto was reclassified and the solar system officially had 8 planets. This was the story from the introduction, but the details behind it are important. The discovery of Pluto in 1930 by Clyde Tombaugh was a sensation. It seemed to complete the solar system. But from the beginning, Pluto was an oddball. It was much, much smaller than the other outer planets. So its orbit was strange. It was highly elliptical and tilted compared to the orbits of the other planets. For part of its orbit, it even crosses inside the orbit of Neptune. As technology improved, astronomers started discovering other objects in the outer solar system in a region called the Kuiper Belt. In the 1990s and early 2000s, they found many of these Kuiper Belt objects, or KBOs. Some were quite large. Then, in 2005, a team led by Mike Brown discovered an object named Eris. Eris was found to be about the same size as Pluto, but about 27% more massive. This created a problem. If Pluto was a planet, then Eris had to be a planet too. And what about the other large KBOs like Makemake and Haumea? Where do you draw the line? Astronomers realized they needed a formal definition of a planet. That led to the 2006 meeting of the International Astronomical Union, IAU. They voted on a 3-part definition. To be a planet, an object must 1. Orbit the Sun 2. Have sufficient mass to assume hydrostatic equilibrium, a nearly round shape. It orbits the Sun, and it is round, but it fails on the 3rd one. Clearing the neighborhood means that the object has become gravitationally dominant in its own orbital zone. It has either swept up or flung away most other objects. Pluto has not done this. It is just one of many objects in the crowded Kuiper Belt. Its mass is only about 7% of the total mass of all the other objects in its orbit. Earth, by contrast, is 1.7 million times more massive than everything else in its orbit combined. So the IAU created a new category for objects like Pluto dwarf planet. A dwarf planet is an object that meets the first 2 criteria but not the 3rd. This is a scientific classification, not a judgment. Pluto is still an incredibly interesting and complex world. The New Horizons mission, which flew past Pluto in 2015, revealed a stunning landscape of nitrogen ice glaciers, vast plains, and towering mountains of water ice. It has a thin atmosphere and 5 moons. It is a fascinating place, but it is not a planet according to the current definition. There are currently 5 officially recognized dwarf planets: Pluto, Eris, Ceres, the largest object in the asteroid belt, Makemake, and Haumea. But there are likely hundreds more waiting to be discovered and classified in the Kuiper Belt. The reclassification of Pluto was controversial, but it reflects a deeper and more complex understanding of our solar system. The solar system isn't just 8 planets and an asteroid belt. It's a rich and diverse place full of different kinds of objects, each with its own story. Number 6. A day on Earth is not exactly 24 hours long. We set our clocks by it. A day has 24 hours, but this is just a convenient human average. The actual time it takes for the Earth to complete one full rotation is not exactly 24 hours. And there are actually 2 different ways to measure a day. The first is the sidereal day. This is the time it takes for the Earth to rotate 360 degrees on its axis relative to the distant stars. A sidereal day is 23 hours, 56 minutes, and 4.091 seconds long. This is the true rotation period of the Earth. The second is the solar day. This is the time it takes for the sun to appear in the same position in the sky again, for example, from one noon to the next. This is what we base our 24-hour day on. A solar day is, on average, 24 hours long. Why are they different? Why is a solar day about 4 minutes longer than a sidereal day? It's because while the Earth is rotating on its axis, it is also orbiting the sun. Every day, the Earth moves about 1 degree along its orbit. So, after the Earth has completed a full 360-degree rotation one sidereal day, it has to rotate a little bit more, about 1 degree extra, for the sun to get back to the same position in the sky. This extra bit of rotation takes about 4 minutes. That's why the solar day is longer. To make things even more complicated, the length of a solar day is not constant. It varies throughout the year. This is because the Earth's orbit is an ellipse, not a circle, and its speed changes. The Earth moves faster when it is closer to the sun in January, and slower when it is farther away in July. This means that the extra amount the Earth has to turn to catch up to the sun changes slightly every day. The 24-hour day is just the average length of a solar day over the course of a whole year. Our system of timekeeping, with its 24-hour days, is a way to keep our clocks synchronized with the sun. But because the Earth's rotation is not perfectly in sync with this average, we have to make adjustments. The Earth's rotation is also gradually slowing down, very slightly, due to the tidal friction from the moon. This means that days are getting longer. About 600 million years ago, a day was only about 22 hours long. The change is tiny, about 1.7 milliseconds per century, but over time it adds up. To keep our atomic clocks, which are extremely precise, in sync with the Earth's slowing rotation, we occasionally have to add a leap second to the year. So our 24-hour day is a useful and necessary simplification. But the real motions of our planet are a bit more complex. The true rotation is a little faster, and the length of a solar day dances around the 24-hour mark all year long. Number 5, there are more than 3 states of matter. In school, we learn about the 3 states of matter: solid, liquid, and gas. You heat a solid, it becomes a liquid. You heat a liquid, it becomes a gas. It's a simple, neat progression, but it's an incomplete picture. There is a 4th state of matter, and it is by far the most common state of matter in the entire universe. That state is plasma. Plasma is often called the 4th state of matter. It's what happens when you keep heating a gas. If you add enough energy to a gas, the electrons are stripped away from their atoms. What you are left with is a superheated soup of free-floating, negatively charged electrons and positively charged atomic nuclei ions. This ionized gas is plasma. It behaves very differently from a normal gas. Because it is made of charged particles, it can conduct electricity and is strongly affected by magnetic fields. On Earth, plasma is relatively rare. We see it in lightning, in the aurora borealis, in neon signs, and in plasma TVs. But in the cosmos, plasma is everywhere. About 99% of the ordinary visible matter in the universe is in the plasma state. Our sun and all the other stars are giant balls of plasma. The solar wind, the stream of particles flowing out from the sun, is plasma. The vast empty spaces between the stars and galaxies are filled with a very thin, diffuse plasma called the interstellar and intergalactic medium. So the solids, liquids, and gases that make up our world and seem so normal to us are actually the rare exception in the grand scheme of the universe. But the story doesn't even end with plasma. Scientists have discovered other, more exotic states of matter that exist at extreme conditions. At temperatures incredibly close to absolute zero, atoms can clump together and begin to act as a single quantum entity. This is called a Bose-Einstein condensate, the 5th state of matter. There are also things like neutron degenerate matter, which is found in the cores of neutron stars and is so dense that a teaspoon of it would weigh billions of tons. There are also theoretical states like quark-gluon plasma, which may have existed in the first moments after the Big Bang. The simple, solid, liquid, gas model is a good starting point for understanding our everyday world. But The universe is a far more extreme and varied place. The cosmos is dominated by a state of matter we barely encounter, and it contains other forms so strange they push the limits of our understanding. Our world is just a tiny, cool corner of a universe that is mostly made of stars. Number 4, the Big Bang was an expansion, not an explosion. The name Big Bang is one of the most memorable in science. It's also one of the most misleading. It conjures up an image of a giant cosmic bomb exploding from a single point into a pre-existing empty space. This is not what the Big Bang Theory describes. The Big Bang was not an explosion in space. It was the expansion of space itself. This is a crucial distinction. There was no outside for the universe to explode into. There was no empty void waiting to be filled. Space-time itself began with the Big Bang and has been expanding ever since. Think of it like a loaf of raisin bread rising in the oven. The dough is space-time and the raisins are galaxies. As the dough expands, all the raisins move farther apart from each other. A raisin in the middle of the loaf sees all the other raisins moving away from it, but a raisin near the edge also sees all the other raisins moving away from it. There is no center to the expansion. Every point is moving away from every other point. In the same way, the universe has no center. The expansion is happening everywhere at once. The evidence for this expansion comes from the light of distant galaxies. In the 1920s, astronomer Edwin Hubble observed that the light from almost all galaxies is redshifted. This means the wavelength of the light is stretched out, making it appear redder. This is a cosmic scale Doppler effect. Just as the pitch of a siren gets lower as it moves away from you, the light from a galaxy gets redshifted as it moves away from us. And Hubble found that the farther away a galaxy is, the faster it is moving away from us. This is the signature of a uniform expansion. Another key piece of evidence is the cosmic microwave background, or CMB. This is a faint glow of radiation that fills the entire universe. It is the leftover heat from the very early universe, a thermal echo of the Big Bang. When the universe was very young, it was incredibly hot and dense. As it expanded, it cooled. The CMB is the light from that early hot state, which has been stretched by the expansion of space over 13.8 billion years until it is now in the microwave part of the spectrum. It is a snapshot of the universe when it was only about 380,000 years old. The Big Bang Theory doesn't describe what banged or what came before it. It describes the process of expansion and cooling from an initial, hot, dense state to the universe we see today. It's the cornerstone of modern cosmology, supported by overwhelming evidence, but the name itself, originally coined as a term of ridicule by an opponent of the theory, has created a powerful but incorrect image in the popular imagination. The beginning of our universe was not a bang, but a rapid, ongoing unfolding of space-time itself. Number 3, stars don't actually twinkle. Twinkle, twinkle, little star. The nursery rhyme is a classic, and when we look up at the night sky, the stars certainly do appear to shimmer and change in brightness. But the stars themselves are not twinkling. They are shining with a mostly steady light. The twinkling is an illusion created entirely by the Earth's atmosphere. The scientific name for this effect is atmospheric scintillation. The light from a star has to travel a vast distance across space to reach us. For almost all of that journey, it travels in a straight line through the vacuum. But for the last 100 miles or so, it has to pass through our atmosphere. Earth's atmosphere is not a calm, uniform medium. It is a turbulent sea of air with constantly moving pockets or cells of different temperatures and densities. These cells act like lenses. As the starlight passes through them, it is bent or refracted. Because the air cells are always moving, the path of the light is constantly changing. For a fraction of a second, more light is bent towards your eye, and the star looks brighter. The next fraction of a second, the light is bent away, and the star looks dimmer. This rapid, random changing of brightness and position is what we perceive as twinkling. You can see a similar effect on a hot day when you look at objects across a hot pavement or a barbecue grill. The heat rising from the surface creates turbulence in the air, making the objects behind it appear to shimmer. This is why stars near the horizon seem to twinkle more than stars directly overhead. When you look at the horizon, you are looking through a much thicker slice of the atmosphere, so there is more turbulence to disturb the light. So why don't planets twinkle? Planets like Venus, Mars, and Jupiter usually shine with a steady light. The reason is that while they are much closer to us than stars, they are still just points of light to the naked eye. But through a telescope, stars still appear as points of light because they are so incredibly far away. Planets, being much closer, appear as tiny disks. The light from a planet comes from this whole disk, not a single point. You can think of the disk as being made up of many, many individual points of light. The light from each of these points is being bent by the atmosphere in different ways. Some are being bent to look brighter, some dimmer, but all these different twinkles average out. The overall brightness of the planet's disk remains relatively constant. Astronauts in orbit above the atmosphere see a completely different sky. For them, the stars are sharp, steady points of light, not twinkling at all. They see the universe without the filter of our planet's restless air. The twinkling of the stars is a reminder that we are looking at the cosmos from the bottom of an ocean of air. Number 2, water is surprisingly common in the solar system. We are taught that Earth is the water planet, a unique blue oasis in an otherwise dry and desolate solar system. And while Earth is certainly the only place we know of with stable liquid water on its surface, the idea that water is rare elsewhere is wrong. And water, mostly in the form of ice, is actually surprisingly abundant throughout our solar system. Let's start with Mars. We have known for a long time that Mars has polar ice caps. These caps are a mixture of water ice and frozen carbon dioxide dry ice. Rovers and orbiters have confirmed that there is a huge amount of water ice buried just below the surface across large parts of the planet. There is evidence that liquid water once flowed freely on Mars, carving out river valleys and filling vast lakes, and maybe even an ocean. Today, the atmosphere is too thin and cold for liquid water to be stable on the surface for long, but there is compelling evidence for seasonal flows of salty brine, which has a lower freezing point. The most exciting places to look for water are not the rocky planets, but the moons of the gas giants. Jupiter's moon Europa is a prime example. Its surface is a shell of water ice crisscrossed with cracks and fissures. Beneath this icy shell, scientists are almost certain there is a vast global ocean of liquid salt water. The ocean is kept liquid by heat generated from tidal forces, the constant stretching and squeezing of the moon by Jupiter's immense gravity. This ocean on Europa may contain more than twice the amount of water in all of Earth's oceans combined. And where there is liquid water and a source of energy, there is the potential for life. Saturn's moon Enceladus is another spectacular case. The Cassini spacecraft flew through plumes of water vapor and ice crystals erupting from giant geysers near the moon's south pole. These plumes are shooting out from a liquid water ocean beneath the ice. The water contains salt and organic molecules, key ingredients for life. Even the moon has water. For a long time, the moon was thought to be completely dry. But missions in the last couple of decades have found water ice hidden in permanently shadowed craters at the lunar poles where the sun never shines. Comets are another source of water. They are often described as dirty snowballs and are composed largely of water ice mixed with rock and dust. Asteroids have also been found to contain water locked up in their minerals. The molecule H2O is one of the most common molecules in the universe. It is formed from hydrogen, the most abundant element, and oxygen, the third most abundant. So we should not be surprised to find it everywhere. The precious, rare thing is not water itself, but a planet at just the right distance from its star, with the right atmosphere and the right geology to allow that water to exist as a liquid on its surface, forming the oceans that gave rise to us. Number one, humans have always been in space. This might sound like a strange statement. The first human in space was Yuri Gagarin in 1961. The first humans on the moon were Neil Armstrong and Buzz Aldrin in 1969. Our physical presence in space is very recent, but in a much deeper, more fundamental way, humanity and all life on Earth has always been a part of space. How we are made of stardust. The atoms that make up our bodies, the planet we live on, and everything we see around us were forged in the hearts of stars that lived and died long before our sun was born. At the beginning of the universe, after the Big Bang, the only elements that existed were the simplest ones: hydrogen, helium, and a tiny amount of lithium. There was no carbon, no oxygen, no iron. The building blocks of life and planets did not exist yet. These heavier elements had to be created, and the only place in the universe hot and dense enough to create them is inside a star. Stars are nuclear fusion factories. In their cores, under immense pressure and temperature, they fuse lighter elements into heavier ones. In a star like our sun spends most of its life fusing hydrogen into helium, but more massive stars go further. When they run out of hydrogen, they start fusing helium into carbon, then carbon into oxygen, neon, and so on, creating progressively heavier elements up to iron. Or iron is the end of the line for normal stellar fusion. Fusing iron doesn't release energy, it consumes it. So when a massive star builds up a core of iron, its furnace goes out. The core collapses catastrophically under its own gravity and then rebounds in a titanic explosion called a supernova. This explosion is one of the most powerful events in the universe. In that brief, violent moment, even heavier elements are created: gold, silver, platinum, uranium. The supernova blasts all these newly created elements, from the carbon made during the star's life to the gold made in its death, out into space. This material, this stardust, enriches the interstellar clouds of gas and dust. Over millions of years, gravity pulls this enriched material together to form new stars and new planetary systems. Our solar system formed from one such cloud about 4.6 billion years ago. The carbon in our DNA, the calcium in our bones, the iron in our blood, the oxygen we breathe, every single atom in our bodies that isn't hydrogen was created inside a star. So when you look up at the night sky, you are not looking at something separate from you. You are looking at your own cosmic origins. The universe is not a place we visit. It is the place we are from. We are a part of the cosmos that has, through a long and complex process, woken up and become aware of itself. In that sense, we have never been anywhere else. We have always been in space.